All right, so my name's Aisha Walcott Bryant. I am a senior technical staff member and research manager at IBM Research based in Nairobi, Kenya. I'm also a program co-chair for this conference, and I am happily your moderator for today. I'm thrilled to be able to introduce Benjamin Rosman as our speaker, a keynote speaker. Benjamin Rosman is a professor in the School of Computer Science and Applied Mathematics at the University of Witwatersrand, South Africa, that's WITS, where he runs the Robotics, Autonomous Intelligence, and Learning Laboratory, RAIL, and is the director of the National eScience Postgraduate Teaching and Training Platform. He received his PhD in informatics from the University of Edinburgh in the UK in 2014, and previously obtained his master's in artificial intelligence, also from the University of Edinburgh. He also has a BSc in computer science and in applied mathematics, also from WITS. His research interests focus primarily on reinforcement learning and decision-making in autonomous systems, specifically on questions of transfer learning and generalization in multitask settings. Benjamin is particularly passionate about growing and strengthening machine learning in Africa, something that I can personally attest to, and is a founder and organizer of the Deep Learning Indaba Machine Learning Summer School. He was a 2017 recipient of a Google Faculty Research Award in Machine Learning and a 2021 recipient of a Google Africa Research Award. And on a personal note, I know Benji from a tip email that I got from Professor Leslie Cabling saying that I need to know this incredible scientist as a roboticist on the continent. And from there, the rest is history. I've been a part of the amazing events that he'll talk about later in his talk today. So join me in welcoming Benjamin Rosman.
Thanks, Aisha, for the introduction. Hi, everyone. I prefer to go by Benji, and I'm from the University of the Witwatersrand in South Africa, and it really is such an honor to be here talking to you all today. I'd like to thank the organizers for this incredible opportunity to give you my thoughts on robots, their capabilities, and the humans around them. So I guess we're all here because we want useful robots. And I think a central theme that keeps coming up, at least in this conference, and I think was particularly well encapsulated by the plenary this morning, is the idea of human-robot collaboration. We really want to build towards a future where robots are maximally helpful in augmenting the capabilities, really, of the humans that they work with. And the way I think about this problem and the work we do in my lab is around really three key principles that we should be placing emphasis on. So firstly, there's flexibility. We want our robots to be able to handle lots of different problems, solve different tasks, in order to be maximally useful. We'd like to have instructability. If our robots can do a variety of different things, it's particularly useful if we can give them these instructions. And ideally, this should be done in a way that's not just limited to an expert giving these instructions, but like the workers working with the robots themselves. And then finally, we're also interested in reliability. If I have some people on, say, a factory floor that give an instruction to the robot, I'd like to know that it actually carries out what I intended it to do and doesn't have some sort of disastrous side effects. So let me give you a bit of an idea of maybe a little more concretely what I'm talking about here. So let's say you've got this robot operating in some sort of office space where you can do all sorts of different things. So here's our robot, and we might have a variety of different tasks that we care about. And we'd like this robot to be able to handle all these different tasks. So for example, maybe what we want is, let's maybe a bit of an old office building, and it has to go and collect mail from the mailroom. And then maybe take this mail to deliver it to people sitting in an office somewhere. And then maybe all the people who didn't get mail are sad, so we should take them all some coffee. And perhaps once we're done with that, we should patrol around to some key points in the environment and see if there's anything interesting going on that we could help out with. And then possibly the whole way along, we should try and avoid breaking some nice decorations in the office space. So this is quite a complicated task we might want. And again, you could imagine that there's some huge variety of such things that we'd like our robot to be able to tackle. Right, so this specifically talks to the flexibility, right? There isn't one specific thing we should be kind of training or kind of hyper-optimizing our robot to deal with here, and so we should handle this flexibility. Again, we want it to be instructable. We'd like that these people working in this office can go and give this robot instructions to do these kinds of complicated tasks. And then finally, we would like this to be reliable. If I tell it, go around and don't break the expensive things I've spent lots of money on, which is possibly the robot itself, I'd like some sort of guarantees that having given that instruction, that's what's going to happen. So, with that in mind, I'm from Africa, as may have been given away already, and specifically South Africa, and specifically Johannesburg. I come from Wits University in Johannesburg, which is also, as it turns out, the home of Gaussian process regression. And we're obviously completely surrounded by wild animals all the time, which incidentally is one of the reasons you should come and work with us. Okay, so what I'm going to talk about today is really two different things. I've kind of got two different talks packed into this one. Firstly, I want to talk to you about this problem that I've just outlined of how we can get our robots to tackle these kinds of challenges. And then secondly, I'm going to talk a bit about some work I've been doing with some colleagues in growing the African community. And hopefully, although these look like two very different problems, hopefully I can convince you that they're both very important and they're tied together in some important ways. All right, so we're going to start off by looking at this robot behavior problem. And if we want some flexibility with our robots, it's kind of useful if they can learn. So ideally, they should be able to learn or adapt to these different tasks that we care about. And so for this, we can pull out our trusty handbook for reinforcement learning and deal with the standard setting. We've got our little robot working in some sort of environment. He gets to take some actions. Based on the actions, the state of the environment changes, and some reward comes along. And again, typically sparse, typically delayed. I think everybody's very familiar with the setting by now. But just to make sure we're all on the same page, we always think about these, or often think about these as MDPs, Markov decision processes. So you've got your robot that exists in its world. There's a number of different states, where the states are your possible configurations of everything of interest in the world. And the robot has some actions available to it. Typically, when you're not looking at this little caricatured version and you're working with a robot, these are obviously going to be high dimensional and continuous and all that kind of thing, but it makes my picture less pretty. And then, given some states and some actions, when you execute an action in a state, you move to some other state, and that's governed by your transition dynamics. And finally, you've got a reward function, which is your way of encoding things that you do and do not want your robot to engage with, and more on this in a bit. What we care about is the policy of your agent. This is the actual behavior, and tells you what it's going to be doing in every state, what actions it will be choosing. What we really care about is the optimal policy, which is the thing that gathers the most reward out of all possible policies you could have. And there's a couple factors that go into this which cause some challenges that we'll dig into. So firstly, your learning is typically trial and error. You've got to try things, see what works, see what doesn't work, and get your reward and learn from there. This poses our first challenge. Our second challenge is the reward function itself. We get some sparse feedback, and that's what we use as the learning signal. Because often policies are difficult to learn and rewards are only given sparsely, we try and learn value functions, which is just an estimate of the goodness of a state and action in a particular situation. Okay, so that's just the basics. But now we do have some challenges that I've outlined here. So firstly, learning is very slow, as is the case with humans or animals trying to learn something, you need a lot of experience when you're trying things, particularly doing some trial and error learning in a rich, complicated space. And sample efficiency in reinforcement learning is typically terrible. You've got to do a lot of learning to be able to solve some sort of complex problem. And now this is obviously compounded by the situation where you might care about this flexibility. You might care about a lot of different tasks. Now you don't want to have to, in the very naive case, be learning each single one. What we'd really like is a situation where we can transfer knowledge between tasks to accelerate this learning on subsequent tasks. So this is a question we look at a lot in my lab, and there's a lot of different ways people have tackled this problem, often called transfer learning. And one of the ways we think about this is maybe we can exploit in some way some symbolic knowledge about the problem and use this to accelerate things. We've got good understandings of what we can do with this kind of knowledge, so let's take advantage of decades of research in that space. So for example, if you can learn skills, if you can learn their preconditions and effects, then these are things that you can use for planning. So specifically, let's say my agent has a skill to move down ladders, and I can learn the preconditions of the skill is that I should be at the top of a ladder, and I can maybe learn this as a classifier. I can then learn the effect or the postcondition of the skill is that I'm at the bottom of the ladder and I'm standing on some ground. You can learn this as a kernel density estimator. Like that gives you a useful piece of knowledge that you can transfer. So then if you're in some environment and you can identify where the skill is useful, you can use that knowledge for planning. Right? So you can then chain together long plans to have your agent do complicated things like move around and pull levers to open doors and pick up keys and unlock doors and go up and down ladders and get to the treasure in the end. Right? And this can just be done then with straightforward planning to solve these complicated problems. Right? So this gives us some useful tools. We can transfer this knowledge that we can learn in some situations and reuse in others. And we can apply this to all sorts of different settings. Again, if you've got skills that say something about being able to open a door or pick up an item or navigate to a door, and if you can learn the preconditions and effects of these skills, again, you can just do some classical planning on top of this to be able to solve some complicated problems. So that gives us some chunks of knowledge in the form of skills, but actually there's more that we could get out of our problem. Right? So possibly we could have our clicker stop working. Okay, so what we can also look at is maybe learning about local interactions of things in an environment, and again, use this for planning. So as a small example, if you've got some sort of domain like a Sokoban problem here, where you've got your agent that needs to push boxes around to particular locations, there's some specific knowledge that you can reuse here, and it's particularly about the interactions of the objects in the environment. So you could look at the situation of maybe your agent's trying to push a box. Now, this isn't just about the fact that the box is in contact with the agent. What you care about here is what's going on the other side of a box. Right? There's going to be different dynamics going on if that's an empty space versus if there's a wall or another obstacle behind it. And turns out you can learn this quite efficiently as and conveniently and interpretably as a set of decision trees. Again, this gives you some knowledge that you can transfer. Now, what's useful in this case is because we're just trying to push boxes, you just need to be able to look to the other side of a box. And so fundamentally, you can get all the information you need about the problem you're trying to solve by just looking at situations with two boxes. So studying this example on the left and learning there, being able to learn these rules then gives you everything you need to be able to solve more complex settings, such as this one, which the optimal solution requires about 200 steps, but you've learned everything about the dynamics that you can then basically zero-shot solve that problem. Okay, so there's a lot that you can do thinking in a slightly more symbolic way to mitigate to some extent the effects of learning all these different tasks from scratch. You can learn this knowledge, you can reuse it in different settings. All right, so that's all well and good, and there's a lot of different solutions to this. But the other problem is that defining tasks is difficult. I think anyone who's worked in reinforcement learning will be very familiar with this from hours of frustration. So we think about our tasks usually as the reward functions. And setting up the reward functions tells us and tells our agent what it's trying to accomplish, right? The desirable and undesirable things. But the problem is that this requires a lot of expert knowledge, right? You've got to fine-tune these reward values. Often this leads to unintended side effects, and this can be a whole mission. And in general, in a complicated setting, this isn't something that's particularly amenable to someone without expert knowledge to sit there and tweaking a +1 here or minus 0.3 there, right? So if we wanted to define a reward function for a task like this, that's complicated. So we can ask the question, can we use this kind of notion of thinking a bit more abstractly or a bit more symbolically to think about our reward functions for these kinds of problems? Now, it's worth at this point asking, what are we actually trying to do? Well, what we want at the core is a human understandable task, right? This is ticking the box of that understandability. And we'd like to be able to define these human understandable tasks that look something like this. Maybe do X and Y simultaneously, or do X until some conditions met, and then do Y, something like that, right? And that really encapsulates this flexibility that we're talking about, right? If you can define these tasks in this way, then that's the kind of knowledge we'd like to be able to plug into our system for our agent to be able to solve this variety of things. And finally, it would be nice if our behavior was verifiable in some theoretical way, right? And that gives us some guarantees then that it's doing what we actually want it to do. So this kind of task description really tells us what we're looking for in these sorts of situations. Now, to deal with this, we need a slightly different way of defining and thinking about our tasks and the processes they're operating over. So imagine you've got this office space. And we can think of this as giving us a kind of background or environment MDP. So you could think that all your tasks might take place in this office space, and they might all share some commonalities, the state space, the actions available to you, the way that your actions have an effect on the world and on yourself. And then there's some underlying reward structure that's useful in this environment, certain things that are just part of the natural way of moving around this space. But if there's certain specific things we care about, so we might have some goals that could be points, they could be regions of interest, things that we might want our robot to end up interacting with, we can think of these as a set of goals, being terminal states. And what's useful to do is think about a slightly different description of a reward function. So if we've got this idea of multiple goals corresponding to our multiple tasks, it's useful to think about the reward as being conditioned not just on state and action and maybe next state, but also the goal that we're trying to achieve. We can change the structure slightly, and we can define it to be that in most places it's going to look like the underlying reward function. But then we can have a negative reward for reaching an unintended goal. So this will say I'm trying to reach something, my agent gets to the wrong place and terminates there, then we penalize it for that, but otherwise it can just follow the structure of the environment. If we've got this kind of reward structure, then we can think that there's something slightly different we're looking for. We're looking for what we call a world policy. Now, normally your policy is just some distribution of your action space conditioned on the state that you're in, but it can also be conditioned on the goal. Right? If you're trying to achieve one thing versus another, that gives you a different idea of what you should be doing next. And similarly, in this case, we can define a world value function, which is your value function that's also conditioned on the goal that you're trying to solve. So we've got these slight modifications to the way that we're thinking about our reward function, our policy, and our value function to think about this multitask scenario. And you can just use, you can learn these with just modifications to your standard algorithms, your DQNs, and so on. Now, why would we go about changing these descriptions? Well, okay, we've got this multitask setting, but turns out if we do that, then it gives us some other opportunities. Specifically, we can perform some operations on our world value functions. So let's say you've got two tasks, or two MDPs in the setting, and they differentiated by this reward function that's slightly different for the different tasks. And for each one, we've got some idea of how we're going to solve it. under the structure, what this lets us do is basically put together a Boolean algebra over your MDPs. Which means that if you can solve these two tasks, you can also compose an MDP which corresponds to solving the task of A or B, or A and B, or not A, right? Where these are the two base tasks that you could care about. And again, if you can do this, you get a homomorphism to give you an algebra over your value functions. What does this mean? This means that if you've solved the tasks previously for A and for B, then you can get this operator that gives you the solution to the MDP A or B, or A and B, or not A. And you can do this without any further learning. Now, you can't do this with the standard definition of value functions. You turn out to get local optima popping up all over the place. So it's really neat that in this framework you get these kinds of abilities. Now, this also gives you some reliability, because with your base skills, you can get these compositions, and these can be done firstly zero shot and provably optimally, given that you've got the optimal base skills below that. So if we've got the situation where your robots learned one skill to get to the bottom left and another skill to get to the top right, you can zero shot get the solution to the problem bottom left or top right. So wherever it starts in the world, it'll go towards the nearest goal. Now, because we've got these three operators, that gives us a Boolean algebra. And so we get this nice effect. We get dimensionality on our side for a change, where given a set of base skills, we get a super-exponential set of tasks that we can solve as defined under this Boolean algebra. Right? So this is really that kind of flexibility that we were looking for in the beginning. But what's more than that is we get these nice intuitive task definitions. So I can look at my agent and say, if I've learned how to pick up blue objects or pick up boxes, I can zero shot get the solution to pick up blue objects or boxes. Or similarly, to get blue objects and boxes, so a blue box, or something that's not a box. Or even more complicated operators like an exclusive OR, give me an object that's blue or a box, but not a blue box. Right? And all of this you get for free, basically, if you've defined your tasks in this way. So this takes us a long way towards this instructability we were looking for at the beginning as well. Right? This is a form that's much easier to give these instructions to your robot. We can take it a step further, actually, and we can plug this into natural language. So we could take it like an input from a human that says something like, pick up the red ball. And we can treat this as a translation task, where we want to translate from this natural language to a Boolean expression. Right? So pick up the red ball would be equivalent to pick up red and pick up ball. And you can learn this through some sort of a transformer, translation model. And then we can do this composition to say that that should give you your value function in the end, and you can just execute that. Right? So we can go from natural language instructions through to your Boolean expressions, and finally to the value functions to solve the task that you're looking to solve, and do this in this kind of super exponential family of tasks built on top of these primitives. So to show you what this looks like, we could have our cute little curry robot operating in a simple environment where you might care about things like going to the bottom or going to the left, or dealing with a closed door. Now, through standard reinforcement learning, you could learn a skill to, say, go into one of the bottom rooms or go into one of the left rooms, right? And those would be two different base skills that you start off with. But now you can use this composition to just say, go to a room that's in the bottom left, right? So that's bottom and left, and we get that zero-shot composition. Right? We can go bottom left and not door, and this is obviously not going to change the solution, but it means we can specify these instructions and it'll get taken into account if it's important. So we can go bottom and not left, which means bottom and right. And we can do things like bottom and not left and not door. So go to the bottom right and avoid the door, and we get this zero-shot solution coming out of our value functions. So again, that's really neat because we get this, this huge explosion in the capabilities of our robot, and we can prove that if the base skills are optimal, then these behaviors are going to be optimal as well. And also much more easily specifiable than just defining this with a bit of reward function hacking. Now, we've also looked at this in a multi-agent setting, specifically in a centralized learning, centralized execution. And here you could imagine you've got two robots, a green one and a red one. And in, say, a first task, the green one can go to any of 3 locations, and the red one goes to one in the bottom left. Your second one might say that the green one's got to go to the top right corner, and the red one can go to any of them. And we can learn these as 2 separate skills. And then we can just take the AND of these 2 tasks, and you get the optimal solution to this coordination problem, which is also fairly handy. So this really deals with all these issues, right? We've got this flexibility, we've got the instructability, and we've got this reliability. And now we can go back to that problem at the beginning. Now this was slightly different. We've got these temporal components to our problem, in that we're chaining things together. We want the mail delivered, which means it's got to be picked up, and then it's got to be dropped off, and then we want coffee delivered, and so on. So it turns out we can extend the same framework and apply it to temporal logics. So you can take this description and express it as something like an LTL, and then translate this into something called a reward machine. And once you've got this machine that describes how the rewards are structured, we can translate that into a task machine, which is basically applying the same kinds of algebras, and so we can execute in this setting. Right, so here if we've learned the base tasks, we can now get this solution to this problem just from your LTL description of what you want. Right, and you'll have your robot collecting all the mail, delivering coffee to everyone left over, and then patrolling around between the desired locations. And as it does everything, it's doing that, avoiding these delicate objects in the environment. So at this point, this compositional reinforcement learning framework has given us the ability to think about flexible settings where you want your robot to be able to solve multiple tasks. It's clearly instructable, and it's reliable in the way it works. Right, so this seems great, like we can do all the things in the world now, but are these 3 principles really sufficient for us to use it everywhere? And I'm pivoting to the second part of my talk, which is, can we rely on this idea, particularly the instructability, to say, is this good enough to be used anywhere? I'm going to use as just a bit of a concrete example this case of a robot driving. So on the left, you can see what a road might look like in Africa. That's not what they all look like. Many have less potholes than roads around here. Not all of them, though. And then on the right, we've got a road in Philadelphia. So there's a number of differences in these situations, even though at the core, what we're doing is the same task. Right, so firstly, the way you give instructions to this might be different. In English, you might say, drive to the tree. In Zulu, you might say, isihlahla. And there's obviously a translation thing going on here, but that makes the task slightly different. Right, you've got other things that happen. You might have an instruction that tells you to stop at the bend in the road. Now, bend in the road might mean something different in these 2 different contexts. Right, in a road that's not perfectly straight, you could see bends everywhere. And so there's a different interpretation of what maybe a bend that's significant enough for stopping at would be in the one situation versus the other. You could also be thinking about different predicates that might not apply in both situations. So certainly in the right, you would probably want to avoid pedestrians, which you might also want to do in the one on the left, but there you're probably more likely to want to avoid elephants than in the second case, unless I just don't know enough about Philadelphia. Right, so this means there's different predicates, there's different aspects of the problem to think about. And then you could also ask other things, like what is permittable, right? So there's clearly differences between driving on the left-hand side of the road and the right-hand side of the road. But, maybe in the one situation, that doesn't really matter. You go down the bit that's most stable, or you drive in the center. In many cases, there's certain roads you're not allowed onto, or you're not allowed onto with certain kinds of vehicles. So typically when you go on safaris, these are the kinds of constraints you come up against. There's also certain roads that you'd have to get permission from certain local peoples to be able to access. There's very different ways that we think about these kinds of problems. And finally, even the behavior of driving is going to be different. The kinds of vehicles you use, whether they're manual or automatic, and the way you drive on a tarred road versus an unpaved road that might be in different states of disrepair. Right? There's very different aspects to these behaviors. So there's a lot of differences in what is fundamentally at its core the same task here, which makes it non-trivial to transfer across from one setting to the other. Right? There's everything from differences in languages to values and priorities, and we need to make sure that these solutions can handle these different cases. So the right way to deal with this is not just to build the technology in one place and parachute it into others. You need local experts. You need people to be thinking about implications for algorithms, for hardware and software. In many cases with the hardware, you work in different temperature and humidity and dust conditions, and your hardware doesn't survive in those kinds of places. Right? So you need these experts to think about this, but you also need local experts that think about linguistics and ethics and policy questions. So what this all fundamentally talks to is you need a local community that can work with these kinds of technologies, whether that's developing them or adapting them. This is really important. But unsurprisingly, community building is very difficult and expensive. So that's what we set out to deal with. And this was something that I've been very heavily involved in, and it's something that I would say I'm possibly, I don't know how to compare my levels of passion for it to robotics, but in about 2017, a group of us came together with the idea of trying to strengthen African machine learning. This was driven by a number of factors. For example, we'd noticed that we'd never seen a paper at the NeurIPS Machine Learning Conference from an African institution. And this is clearly a problem, as I've addressed here, that it means a lot of these technologies aren't directly applicable, and you're missing out on 1 billion people and the way that they can be involved in what's happening with technology generally. And this led to a movement that we called the Deep Learning Indaba. Indaba is a word in Zulu or Xhosa for a meeting or a gathering. And so the idea was that we could start building a community of people working in machine learning across Africa. So this was kind of the third iteration of our committee. We started with 5 of us, grew to 8, grew to 13, and then more people than I can count. I had a lot more hair in this photo. And really, this was this group of us that were mainly South African, had all studied abroad, many were working abroad at places like Google and DeepMind, and we wanted to do something to help grow our local community. Because really, it's one thing to say your country is not represented, but if your entire continent isn't, then that's something of a problem. And our idea was to put together an intense state-of-the-art machine learning workshop for African researchers. And we had a goal. We'd find 30 or 40 people across the continent that would care about these things. So the idea was that we're all going to fly out. We're going to organize a few-day event, ended up being a 6-day event, where we'd all give talks and bring in as many people as we could. So our first event was held at my university, University of the Witwatersrand, and we had about 330 attendees, and probably double the applicants. So we had to go through quite a rigorous peer review process with multiple reviewers on each applicant and end up being double blind and everything. And this was to get these attendees. We had people from, I think it was about 22 different African countries represented, and from all levels of careers, mainly from masters and PhDs, academics, and then people in industry and startups. It was very successful. We had an event the next year in Stellenbosch, just outside of Cape Town, where we had about 550 people from across the continent. Then the next year we moved out of South Africa and we went to Kenyatta University outside of Nairobi in Kenya, and there we had about 700 people. And then COVID killed all our momentum. But I'm glad to say we'll be having the next one in Tunisia this year, in August. So this community is clearly growing, and there's a lot of interest in this. And we can see this even in the number of applicants that we've had over the years. We can see some steady growth. It's usually been 2 to 3 times the number of applicants to the number of people that we can host. And that's usually constrained by a couple of things. One, the size of the venue, and also we go to great lengths to fund whatever students we can, which is really the bulk of our budget. There have been many cases where, so we try and fund people from as many different countries as we can. We've had cases where we'd get an endless supply of emails that went along the lines of, there was a student who emailed us from Ethiopia, and he was accepted, and he said this is one of the greatest things that ever happened to him, but unfortunately he can't come to South Africa because the flight ticket is 3 months of his father's salary. Right, so you get all these heartbreaking messages. So the first year we managed to completely sponsor about 70 students from across Africa. We've been trying to grow that steadily every year. I think now we try for about 200. So the Indaba itself, at its core, we have these technical sessions that include plenary talks, as well as deep dives into different topics such as computer vision, reinforcement learning, and so on. We try to get experts from around the world, and generally they fly out on their own dime to be involved in this. And we try and get the highest profile people we can to come and talk to people, maintaining all the diversity that we're looking for and so on. And with all of our deep dives, we couple this with these kind of technical lab sessions where we've got teams of people that have prepared lab material. We've got tutors from across the continent, and it means that our attendees can really get into the nuts and bolts of the stuff that they've been learning about. And then because we're trying to build a community, the social events are very important as well. And so you can't have a good tech conference without good social events. And then, as I said, we try and support as many students as we can as a really key critical aspect of this. So I want to just play a few-minute video for you guys that we made just off the tail end of the first event, just to give you an idea of what it was about and what our ambitions for the event were.
This is the first workshop of its kind where young people, people from industry, from governments, are all coming together to learn, to debate, to network the advances in machine learning and AI and how Africans will contribute to that area of science.
The trick is to take the combined knowledge of the world and deploy it to our circumstances. But as we deploy it to our circumstances, we innovate and we recontribute to the world. That's what this is about.
This has been an incredible opportunity. I mean, we've got a collection of about 300 nerds from across Africa.
We have people from over 30 different countries, 22 in particular being from the African continent.
I'm hoping to find new tools to solve my problems in terms of my research studies, because I'm working on applying machine learning in radio astronomy.
This conference has really increased my passion for deep learning and machine learning.
The Indaba has been held over 6 days, over which we as a community have come together to discuss, debate, network, and learn from each other through practicals where people actually got some hands-on experience getting their core concepts in deep learning and machine learning.
Having the chance to learn from people from the likes of Google DeepMind, which is an incredible opportunity that you wouldn't really get very often in Africa. So we're pretty privileged and we're loving every second of it.
Now I'm getting to see an overview of everything and discovering where the gaps in my knowledge are. So it's inspiring for me to go back home and fill in those gaps for myself.
It will enable me with the knowledge and understanding to finish my PhD as soon as possible.
We had an opening event which was really exciting and we had a lot of fun. It was interesting to know that nerds aren't only about coding and sitting at machines 24/7, but we also do have some fun.
Deep learning and machine learning that have been mainly made for problems in the global north. And we as Africans have continued to be receivers of those advances. Events like this Indaba and subsequent ones will change that. We will become contributors and active shapers to use machine learning and artificial intelligence to solve the problems affecting our communities and our continent.
I look forward to next year's Indaba. I hope it'll be bigger and better. And to anyone who may be interested, I really wish that you will try your luck and try to be here with us and come learn more about machine learning and deep learning.
So we've done some experiments on this every year, and we've tried different things with the aim of innovating. So for example, something that's become a major feature is we've got what we call the Africa Research Day. That's one of our poster sessions under the trees. We encourage all our attendees to come and present posters and have discussions about their work. We've gone from this mode of having all these large talks to different kinds of parallel tracks that started with splitting things up into beginner and advanced levels, and now we have that people in our community can propose different workshops and organize those and run with those. We've always pushed very hard for women in machine learning events, and we've been introducing more and more events around ethics, policy, thinking about startups. Actually, some of our most heavily subscribed events are how to write good papers and how to apply for PhDs in other countries. We really view the idea of growing as being based on three elements. One is community, two is leadership, and three is recognition of excellence. So the community, that's what the Indaba is all about. And it's an interesting experience when you have the Indaba and people from different countries and backgrounds come up and hug each other and say, haven't seen you in ages. You know, it's what we have at conferences all the time. But none of us had ever seen this happening in Africa in any way at all before. In terms of leadership, one of the programs that we started is called the Indaba X. And after the first event, we scraped together some money and had a call for proposals for people to host satellite events in their own countries. And so we had this whole proposal process where you had to talk about how you would structure it, how you'd appeal to get diversity in your event, and so on. If we had multiple ones from the same country, we'd introduce them to each other and let them have an event, and we ended up with events. We've now supported events in more than half of Africa. And many of these people have then, in subsequent years, gone on to join the organizing committee of the main event. And then finally, we also look at trying to reward excellence and recognize excellence. So we have these awards for things like impactful projects in your community and dissertation awards for self or peer-nominated master's and PhD dissertations. And we view these as the three key ingredients. And through things like the Indaba X program, we've had about 3,000 more people coming into the network that we've been able to reach, which we couldn't have just reached through the main central Indaba. At the moment, we're sitting on average about 32% women at these events, and we're trying to push these numbers all the time. And the impact's been felt in a lot of different ways. In terms of students themselves, we're now seeing papers at all the big events and more of these, which is really exciting. We've had quite big delegations of people going to conferences like NeurIPS, which has been really exciting. We've been doing a lot of kind of co-supervision. So you'll have students in Sudan, for example, that are really good and don't have access to any supervisors, and now they've got a network of people that can externally supervise their projects, if not take them into their universities. We've seen a lot of new startups coming out, people getting jobs in the field, and so on. There's been a lot of networks being built, and this has ranged from collaborations that many of us have benefited from, collaborations with people in the rest of the world and also internally within Africa. And we've seen a number of other interesting things happen. So for example, some of the people involved in the community started something called Masakane, which is a kind of loose collective of people working on natural language processing in Africa to tackle problems around under-resourced languages and so on. We've seen a lot of new courses and programs start up at a whole lot of different institutions. For example, there's the African Masters in Machine Intelligence, which is being run out of Kigali, Rwanda, supported completely by Google and Facebook, which they say is one of the hardest programs to get into in the world. And I've had the honor of teaching there, and the students are absolutely incredible. And all sorts of new funding sources as well. There's things like the Lacuna Fund and AI4D that are coming up to support projects where people are trying to apply machine learning to their local projects, whether that's trying to build tools for local farmers to diagnose problems with like diseases in their cassava plants, or doing translations to African languages and so on. We've got this kind of support now starting to happen in the, on the continent. And something else that's been really inspiring is that it's having a broader impact across Africa. So there's now other movements that have started in other places, and we encourage other people to think about this as well. We've been involved in giving a bit of guidance and help on some of these. So for example, in South America, there's Kipu, that's also started up as a similar movement. There's the Eastern European Machine Learning, and there's the Southeast Asian Machine Learning School, all with similar kinds of ambitions for different parts of the world. And hopefully, as I made the case, this is important, because if we want to build these kinds of technologies, we need to make sure that they can be actually used, not just in a place like the US, but that everyone else can benefit from this as well. So really, all of this coming together, what we want is this world of human-robot collaboration. But the world also needs to be embracing the human-human collaboration side of everything for this to be really successful, and us not to end up with situations where we've got terrible divides between different parts of the world. And I think the way we unlock this is on the robot side of things. We've got to think about properties such as flexibility, instructability, reliability, to be able to put these technologies in the hands of the people that can actually use them, that aren't just the technical experts. But we need to make sure there's local technical experts to really complete this transfer of knowledge to these different places. And this can only be done through these kinds of movements to consciously build up the communities in certain parts of the world. I'm just going to throw out here a shameless plug that we're looking for postdocs in RL and robotics in my lab, and my department is expanding, and we're looking for faculty from lecturer up to associate professor in areas like data science, applied maths, machine learning. So you should all apply for that and come and see all the animals and things. And with that, I'm going to wrap up. I want to thank my labs, especially the students that helped on all the projects that I've spoken about today, and our international collaborators, and also the rest of the community of the Deep Learning Indaba. Thanks so much.